Hello, I am Chong Lee, the president of EQS and joint seminar manager of QISCA. As continued for the Journal Club, Beomjoon will be presenting a talk titled How to Read Out Superconducting Qubits, sharing insights from the papers Quantum Computing, an Introduction for Microwave Engineers by Joseph Bardeen and A Quantum Engineer's Guide to Superconducting Qubits by Krantz. Please join me in welcoming Beomjoon to the stage once more.
Okay. Well, thank you for your kind introduction again. Yeah, my name is Beomjoon Chae, and I'm an undergraduate student in Electrical and Computer Engineering Department at Seoul National University. So yeah, as a journal club seminar, I'm going to talk about how to read out superconducting qubits. So yeah, actually, I gave some basics. I gave some presentation on introduction to quantum optics, and yeah, and the concepts that I mentioned in those kind of basic seminars are also widely used in the field of superconducting qubits. So yeah, so I'm going to briefly review the quantum optics and yeah. Yes, I'm going to briefly review the quantum optics and also like, yes, in the, yeah, how can I express, yes, in like LC resonators, which is widely used in electrical circuits, can also be, yes, can also be described in like in a quantum mechanical manner. And so, and this is also an important concept in superconducting qubits. So I'm going to introduce this. And as a, yes, and maybe the one of the big characteristic in this field is that we use Josephson junction as kind of a inductor, as kind of a inductive electric circuit component. So I'm going to express this, I'm going to explain this, and finally I'm going to introduce how to read out qubits using the method called dispersive readouts. So briefly, I'm going to review the quantum optics. So yeah, if we consider some kind of cavity or like, yes, if we consider some kind of cavity, yes, some structures that we can store electromagnetic energy, then the energy stored in the cavity can be described in this form. And since the energy stored in the cavity has the form similar to the one of quantum harmonic oscillators. So we can describe the dynamics of some electromagnetic cavity. Yes, using the method we used in quantum harmonic oscillators. So using second quantization method, we can describe the Hamiltonian in this way, but here the analyzation and creation operator is applied to the state of the cavity instead of the original quantum mechanical oscillator. So as a result, when there is a atom, the two-level system inside the cavity, then the quantum mechanical states and the electromagnetic field in the cavity are going to interact with each other. And those kind of interactions can be described with Jaynes-Cummings Hamiltonian. So the Jaynes-Cummings Hamiltonian looks like this, and the first term is it represents the energy stored in the cavity itself, and the second term represents the two-level atom, and the third term represents the interaction between the cavity and the atom. So yes, this is some kind of brief review of quantum optics, and let's move on. Yes, so as I told you that the energy stored, because the energy stored in the electromagnetic cavity has the similar form to the one of quantum harmonic oscillator, we can use these kind of representations. But well, in case of LC resonators, like this kind of resonating circuits, we can also apply the method used for quantum harmonic oscillators. In this case, if we denote the magnetic flux of LC resonator in this way and the electric charge as Q, then the energy stored in the resonator is going to be like this. And considering the circuit theory, Q is going to be proportional to the time derivative of magnetic flux. So that means this is going to be this is going to be the quantity corresponding to position, and this is going to be the quantity corresponding to the momentum. And yeah, so we can use the method. We can use the method for harmonic oscillator to describe the dynamics of LC resonators. So if we denote the resonant frequency of the LC resonator in this, if we denote the inductor as L and if we denote the capacitor as C, then the resonant frequency of the LC resonator is going to be like this. And in this case, the Hamiltonian is we can describe the dynamics as a quantum harmonic oscillator, then the Hamiltonian is going to be like this. So when we draw a figure of energy modes of the LC resonator, then it is going to be like this. So yes, this is the quantum mechanical description of LC resonator circuits. And now we are going to think about how a Josephson junction behaves in these kind of circuits, Well, Josephson junction, like in the field of superconducting qubits, the Josephson junction play a role of a inductor, but the inductor is going to the inductor is a bit weird. It's a weird inductor or nonlinear inductor. So like, yes, if the magnetic flux of the Josephson junction is denoted as pi, and then, well, if it is a normal inductor, then the how can I express the current and the voltage of the inductor is going to be described in this way. But in the case of Josephson junction, the current and the voltage of the Josephson junction is going to be described like this. So as you can see, there's some kind of weird difference between them. So yes, the current of Josephson junction is not directly proportional to the magnetic flux pi. Well, instead, the current is proportional to the sine of something of pi. So the energy difference is not gonna be how can I express the energy difference, the gap between two energy states is not constant for the resonator with the Josephson junction. These kind of LC resonator, in other words, this kind of LC resonator has the energy levels which are quite different from the previous diagram. And if you draw the diagram, then it is going to be like this. And yeah, so then we want to how can we understand the behavior of Josephson junction? So considering the definition of inductance, the inductance of Josephson junction is going to be like this. And if we considering the relation between the current and magnetic flux, the inductance is going to be derived like this. So yeah, so that is why the Josephson junction is called as a nonlinear inductor. So as we can expect, the energy level of the Josephson junction is not the same as the one for not the same as the one for original LC resonator. And the energy level is if we solve the corresponding Schrödinger equation for superconducting qubits with Josephson junction, then we can obtain the energies like this. Well, I'm going to skip the detailed mathematical procedures. So yeah, so as you can see, there is some linear term, but because of the nonlinearity of Josephson junction, there is some kind of like nonlinearity, or maybe in other literatures, it is called some unharmonicity. So yeah, so you can see that the energy difference between each two states, between the adjacent two states are not the same, not the same. So yeah, this is how we can describe Josephson junction as a nonlinear inductor. And then maybe you guys ask a question, why do we need such kind of nonlinearity of Josephson junction? So yes, this is like this. When we make a qubit with an LC resonator with the Josephson junction, then anyway, we simply denote a qubit as a two-level system. Then anyway, if we make a superconducting qubit using Josephson junction, then we just interested in the first two states, one for ground states and the other one for excited states. And we just want to make some like transition only between the two states. But if we make a qubit with just a simple LC resonator, then the energy difference between the two agent states are going to be all the same. So if we try to deliver some electromagnetic field to make some transition between 0 state and 1 state, and it also induce the transition between 1 state and 2 state, 2 state and 3 state, 3 state and 4 states, etc. So if we add the Josephson junction as a nonlinear inductor, then yes, the energy difference between the two qubit states is going to be all are going to be different. So if we apply some electromagnetic field or some other methods to induce the transition between them, then there is no transition between other states like 1 and 2, 2 and 3, 3 and 4, etc. So if we use Josephson junction as an inductor in the superconducting qubit, then we can consider those kind of nonlinear LC resonator as a two-level system or a qubit. So this is how we make a superconducting qubit. So anyway, then that means we have two kinds of resonators. One is just a normal LC resonator, and the other one is the LC resonator with Josephson junction. And yes, the first one is then the first one is just a normal LC resonator following the dynamics similar to quantum harmonic oscillator. Then the Hamiltonian of the normal resonator is going to be like this. But if we use Josephson junction, I told you that we can consider this kind of resonator as a two-level system, and that means we can describe the LC resonator with Josephson junction with these kind of Hamiltonian. So like two-level systems. And if so this is two kinds of resonators. And yeah, when we have two different resonators, then we can use some other capacitors to couple the two resonators, like by using a capacitor between the two LC resonators, we can make the two resonators couple, like exchange their energies to each other. So, and also by increasing the value of C, the capacitor, if we increase the size of the capacitor, then we can make the coupling strength much more stronger. So, well, as I told you that the LC resonator with superconducting qubits can be considered as a two-level system, or like it's just kind of a LC resonator. So maybe we can couple the two different kind of resonators using a capacitor. And well, so we can consider this as a two-level system, and we can consider this as a harmonic resonator or like cavity. So the dynamics of the overall system can be described using Jane's Cummings Hamiltonian in this way. So yeah, and well, the coupling strength can be described in this way. Well, I will just skip the detailed procedure of how to derive this quantity, but as you can see, the coupling strength is directly proportional to the capacitor Cg. So yes, if we increase the capacitance, then the coupling strength becomes much more higher. So if the resonant frequency of the two-level system of this nonlinear LC resonator and another normal LC resonator, if those resonant frequencies if the difference between those resonant frequencies is quite small, then the two-level systems can directly exchange their energies to each other. Yeah, to each other. And the energy levels hybridize. And so, well, actually, you can just keep in mind that if the difference of the resonant frequencies is small, then they can directly exchange their energies. But if the difference between the two resonant frequency is much more higher, then there is no direct exchange of energies. However, like but instead, depending on its state, the qubit, there is some kind of other interesting phenomenon, which is like this. Depending on its states, the qubit pushed the normal resonator's resonant frequency. Yes, it's called dispersive shift, and it's going to be like this. If the two-level system or the qubit has the state zero, then the resonant frequency of this harmonic resonator is going to be like omega. Sorry. So it's like this. Depending on the state of the two levels of these qubit or two-level system, the resonant frequency of the harmonic resonator becomes different. Yeah, so this is called dispersive frequency shifts. And yeah, can you see okay. Yes, well, the expression in the light gray rectangle is the original James Cummings Hamiltonian. And if we add some additional condition that the two resonant frequencies is different, hugely different, then we can derive we can derive the Hamiltonian of the system in this way, the expression in the red rectangle. So yeah, so as you can see, the term of the Hamiltonian, the first term of the Hamiltonian, the equation in the red rectangle looks like this, and that means the frequency of the resonator, the harmonic resonator, depends on the state of the qubit. So we can determine the state of the qubit by figuring out the resonant frequency of the harmonic resonator. It's like this. If we measure the resonant frequency of the harmonic resonator and it becomes something, then we can figure out the state of the qubit coupled to the resonator. So yeah, this is how those kind of two resonators looks like. So like, how can I express this? Yeah, so like the cross, the cross, the cross, yes, the, the cross in the figure is a superconducting qubit, which also can be represented as a LC resonator, nonlinear LC resonator. And the other thing in the above of the cross symbol is the readout resonator, which is just a normal resonator. So yes, in this way, we can detect or we can read out the state of the qubit. And because the frequency shift of the resonant frequency shift of the harmonic resonator is called dispersive shift. So this kind of readout scheme is called a dispersive readout. And since the normal resonator is used to read out the qubit, so this kind of normal resonator is also called readout resonator. So yes, the detailed scheme of the dispersive readout is like this. To figure out the resonant frequency of the readout resonator, we can measure the reflected signal from those kind of systems. Yes, this is like this. When we apply some electromagnetic signals to the system, well, which is denoted as A1, then there is some kind of reflected signals from the system, which is denoted as B1. Then after we obtain the B1, then we can figure out how the B1 looks like. How the B1 looks like. Like, yes, we draw the spectrum of the signal B1, and well, depending on the state of the qubits, the resonant frequency is going to be different, which means as you can see in the right bottom of this page, the figure is the shape of the plot is going to be different. So based on those kind of informations, we can figure out what is the state inside the qubit. Then why do we use readout resonators? Well, why do we read out resonators? Well, if we directly measure the state of the qubit with no readout resonator, well, we can imagine that figure on the right top of the page. So in this case, the problem is that if we want to speed up the measurement procedure by increasing the capacitor C kappa, then at the same time, the lifetime is going to be shortened. And that means there is a huge trade-off between the speed of the measurement and the lifetime of the qubit. So that is why we use readout resonators. By using readout resonators coupled to the qubit, we can detect the state of the qubit with no concern of the lifetime of the qubit. So yes, this is all I prepared for the Journal Club seminar. And summary, the dynamics of LC resonator circuits can also be understood as the one of quantum harmonic oscillators. And Josephson junctions play a role of nonlinear inductors in resonator circuits. And we can consider an LC resonator with the Josephson junction as a two-level system, or we can just simply call it as a qubit. So LC resonators can be coupled using a capacitor, and we can change the coupling strength by changing the size of the capacitor. And in quantum optics, we can describe the coupling between the normal LC resonator and the nonlinear LC resonator with Josephson junction by using Jaynes-Cummings Hamiltonian. So, well, if the resonant frequency between the normal LC resonator and the nonlinear LC resonator with Josephson junction is hugely different, then there is no direct energy exchange between the resonators. Rather, the qubit has some effects on the resonant frequency of the resonator, and which is called dispersive shift. And based on the principle of dispersive shift, we can read out the state of the superconducting qubit, which is called a dispersive readout. So yes, this is all I prepared for Journal Club seminar. So if you have any questions, then feel free to ask me your questions.